Today we will discuss a really cool topic, Gaussian processes. It's a way more flexible tool for regression and related problems than what we've seen so far. Also happens to be one of the tools that both machine learning folks and statisticians like. Yeah, it has the favor of both communities. It's also a little unintuitive, probably at the first encounter. And there will be plenty of equations today. And I did not want you to get lost in the copying down of equations. So all of this is today in the public document. And we will try and go through these derivations together. So what have we done so far? Previously, when we talk about linear regression, we had this very simple model there. We assumed that the true predictions y, or the true values y, are a linear function of space plus possibly some noise. Today, we'll make a radically different assumption. Today, we will assume that our observations are the realization of a multivariate Gaussian. So y, this tilde means is distributed according to. N is a normal distribution with mean mu and covariance structure sigma. We also assume for starters that both the mean and this covariance structure are known. Now, in real problems, we either have to make an educated guess or we have to try and fit them to the data. These are non-trivial problems for reasons that I will explain. But for now, we assume that mu and sigma are known. Now, this is very well to make that assumption for the observations that we do have. But what if we now want to make predictions at other locations x? So if we want to interpolate or extrapolate, we assume the existence of a so-called Gaussian process. Now, what is a Gaussian process? A Gaussian process is an infinite collection of random variables. And these random variables are indexed by their spatial location. So we can have Gaussian processes in one dimension or in p dimensions. And why they're called Gaussian process is because we have the requirement that if we take any finite subset, so if we sample this Gaussian process at a few specific locations, and if we look at the joint distributions of these selected random variables, a finite set of random variables, then in Gaussian processes, we make the assumption that these random variables will be jointly normally distributed. So they have a joint Gaussian distribution. By the way, this is the difference between a stochastic or a Gaussian process and a Gaussian random field. In a Gaussian random field, we would assume that we have a finite number of random variables or a countably infinite number. So then the random variables would be located at let's say at the corners of a Cartesian lattice. But here we assume that we have this uncountably infinite number of random variables indexed by space. I'll show you pictures in a moment. Now, what about this covariance structure sigma? Effectively, all we need is that this matrix is symmetric and positive semi-definite, meaning it has no negative eigenvalues. This in turn means that we can pretend that this is something like XX transpose. So we can take this matrix sigma from whoever gives it to us, prior knowledge, neural network, whatever, and these, even between random variables at a fixed distance, in principle, at different points in space, the amount of correlation between them could be different for different locations in space. In practice, however, a very standard assumption is that the process does not change its nature over space. So it has the same amount of correlation at a given distance, no matter where we are in space. So in other words, we then make the assumption that the covariance between two locations, or the random variables at two locations, okay, I think I should have written here, let's say the random variable y of x and y of x prime, that this is a function that depends only on the relative distance of these coordinates, x and x prime. Now there are many such functions k. They need to, again, be symmetric, positive, semi-definite. These are also called Mercer kernels. And there is a large collection of Mercer kernels that you can also combine to create new kernels. Okay, pictures at last. So, here's a picture of what assumption are we making. Here are some realizations of one-dimensional Gaussian processes. On the top is one particular Gaussian process, and you see on the right-hand side the covariance structure that was assumed. So here, as we consider 2 points x and x prime, if they are close by, we assume that they have a large amount of correlation. If they are farther away from each other, we assume that they have a small correlation. Indeed, this shape here has the shape of a Gaussian kernel, but it has nothing to do with the Gaussian kernel. Or there's no probabilistic interpretation associated with this particular choice, which is why this is here called RBF, or radial basis function. So the radial basis function kernel does have the shape of e to the minus, and then we have some parameter, I'm calling it kappa here, x minus x prime squared. So this looks very much like a Gaussian, but it is not a Gaussian. It's merely, the shape that you see here, a radial basis function. And here in this top picture, you see a few realizations of this particular Gaussian process. So this is a Gaussian process with a mean 0, so mu equals 0, and the covariance given by this radial basis function kernel. So what does that mean? You see any finite collection of random variables. Let's maybe pick this one, and let's pick that one, and let's pick that one. So each random variable individually would have a Gaussian distribution. So this would be Gaussian distributed. This one would be Gaussian distributed. Here, sorry for the overlap. This one would also be Gaussian distributed. Yeah, so the marginal distributions are all Gaussian. But for this to be a Gaussian process, we also need these three to be jointly normally distributed. And in fact, a subset of random variables that we pick should be jointly normally distributed here. And, well, a boring stochastic process would be one where the correlation structure would look as follows. We simply have some variance, and then it would continue at 0 elsewhere. Can you describe what a realization for this red kernel would look like? Yeah? Yeah, it would be perfect white noise. Yeah? It would be, if I'm trying to draw the white noise here, this picture would be wrong because, if I zoom in, this still looks like it's continuous, and in fact it's not. Yeah? What we see with this red covariance function here is that, yes, we have some variance at the origin, so we have a finite spread, but as soon as I go epsilon away in space, the correlation drops to 0, and it stays 0 at larger distances. So this would be perfect white noise, which, however, has a Gaussian distribution. Now here we have introduced some structure. So this would be, to stay in this, this vocabulary, this would be colored noise, which we see here. All of these realizations can be considered as colored noise. So now, so far we have no observations in the game at all. This is just to show you, to give an illustration for what a Gaussian process could look like. Now let's change the kernel. Let's take this kernel at the bottom here. Here this kernel is e to the minus, again, some kappa. And now I'm taking x minus x prime, but not to the squared. So it's just an exponential decay here, one-sided exponential decay. And now the realizations look like this. So the marginals are the same. So if I consider these three random variables here, because I can read off at the origin, so the variance of this Gaussian process is the covariance read off at x, and then x prime equals x. So of the variance here at the origin, this is going to be the variance. And the variance in these two Gaussian processes is the same. So I know that the marginal distributions, they will be the identical ones as above. So I'm just going to copy the ones from up here. The marginal distributions are the very same. The joint distributions of these three that I've picked here is still multivariate normal. However, we see that we clearly have a different degree of correlation between points that are close by. Yeah, so if we look at the long range, and if we look at one of these realizations here, so there is some correlation at long distance, but not too much. We can read it off at this distance here. We have some correlation, but not too much. Actually, this is the same. So we could say that the long-range behavior of these two Gaussian processes is the same. But if we look at small distances, the short-range behavior is very different. And so, in other words, the big difference between these two curves is mainly here at the origin. And this leads to one of these Gaussian processes being much smoother than the other. Do I reload or do I recover? Okay, reload was good. So you see as we zoom in that this top process is very smooth, the bottom process is very rough. And this is a consequence of this modeling assumption that we're making by choosing one particular covariance structure. All right, these were 1D examples. Let me give you 2D examples. And you've seen these before in this course. I here have, in the top, I have two realizations of the same Gaussian process. Also, this one has a mean of 0, and the kernel that you see not drawn quite to scale that you see here. So this is, again, the RBF kernel, and we see that the RBF kernel gives rise to very smooth realizations. In the bottom, this is, so we had here the RBF kernel. Here we also use the RBF kernel, but this constant kappa has changed. So the RBF kernel has become much narrower. And You see that while here we have substantial long-range correlation, here we have very little long-range correlation. And accordingly, these realizations on the bottom, well, don't have correlation at some larger distance. Yes, question?
Is the function of the response always continuous as long as we don't have a delta function? Or?
Very good. Whenever we add whenever we have a jump at the origin, so I'm trying to draw it like this. Yeah? Whenever we have a jump at the origin, then these functions become discontinuous, and otherwise they are continuous, but the roughness of these functions depends on the behavior at the origin. So how many derivatives exist of this covariance function at the origin. So at the bottom, this is again this exponentially decaying kernel. We see that it has a fairly long range. Yeah? So in terms of the long range correlations, it's like this first two-dimensional example, like the one that you see on top. But because it looks different at the origin, these processes here are microscopically rough. So they look rough at this scale, and if I zoom in, they have a fractal nature essentially. Yeah? So they stay rough at all scales, like Brownian motion. And this is not accidental, because indeed, if we use here one-sided exponential covariance, the realizations that we get out are Ornstein-Uhlenbeck processes. So random walks essentially. Here random walks that return to the that are biased to return to the mean. So these were pictures of Gaussian processes. So this is the prior assumption that we're making. Depending on the choice of mu that we make, depending on the choice of covariance structure sigma that we make, we implicitly make the assumption that our observations have been sampled from a Gaussian process like this, or like that, or like that. But so far, observations have not entered in this game at all. Okay? Now, enter observations. Let me... Okay, so what is wanted at inference time is we want the conditional distribution of some random variables y, u. I have used subscript u here to say unlabeled. Yeah, we don't have observations here. But we know where we ask these questions. Yeah? So the locations xu are known. So I could say at what we want is the conditional distribution of yu at some given locations xu. So xu is where we want to ask questions, or where we want to make predictions. We want to figure out what is this conditional distribution given the observations that we do have. The observations that we do have, I call them YL, L for labeled. And of course, we also know where in space these observations come from. These are at sites or at locations XL. So if I try to write it somewhat properly, at some point we said for random variables we should really use capital letters and so on. I'm not doing it today except in this equation here, where I'm saying that we are looking for the distribution of my random variable, or my set of random variables yu. Those are the random variables where I don't have labels. I'm asking these questions at locations xu, which are known. And now this vertical bar here as always means I condition on. So I'm interested in this distribution given. And now on the right-hand side, the random variables yl, capital YL, are known to have realizations small yl. Okay? And because this is rather many letters to write, today I'm just going to abbreviate this with yu given yl. Okay, this is a shortcut for everything written on the left-hand side. All right, let's try and solve this graphically. I have the following problem. I have two observations. So this is a one-dimensional problem. Yeah, I have two observations. My observations here are 0 and 1. And I'm interested in making a prediction at this x value here. Yeah, so I would like to know, how to continue. If I were to make linear regression, my prediction would be this. But now, under the model we're discussing today, what is it? Should it be more or less? We will find out. So, as always, when we talk about Gaussian processes, I need to assume a mean and a covariance structure. So here I'm going to assume that mu equals 0. And I'm saying that my kernel at two locations, x and x prime, is going to be the RBF kernel of x minus x prime. Okay, in one dimension, it's enough to write it like that, but okay, good. And what I've written here is just, a reminder, my observation y at the first site, at the location here, I call the first location x1 was 0, and here at my location x2 it was 1, and y of x3 is unknown. So this is my y unknown, and these here are the yl, the labeled ones. Now we said that if I assume that this is a Gaussian process, then any finite number of random variables, like these three here, should have a joint Gaussian distribution. Yes, question?
Does mu always have to be shared across all observations?
Mu can be different in principle for all points. For now, I'm just assuming it to be 0, but it can be different in principle. Okay, now what does this Gaussian process look like? I can say that, overall, it would look like y minus mu transposed, sigma minus 1, y minus mu, and okay, and then there is an exponential, and there's a minus 1/2, and there's some constant that I'm not interested in. Okay. Now I said that here I'm assuming that mu is 0, so I'm saying this is 0, this is 0, and this matrix sigma here we can compute very concretely. Okay, so let's say that my RBF kernel is simply e to the minus x prime squared. So here I've set this constant kappa to 1. Okay, and then we're interested in these distances. So what does it look like at 0, 1, and 2? I have my RBF kernel here, looking broadly like this. And now I can fill in my covariance matrix. So I can say that sigma is going to be, at these, in the diagonals, e to the 0 is 1. E to the 0 is 1. Okay, and then at a distance of 1, we have e to the minus 1 or 1 over e. What is this in numbers? I don't know. I would like to put a real, well, I'm just going to write 1 over e here. 1 over e, 1 over e, 1 over e. And here it is e to the minus 2, so 1 over e squared, 1 over e squared. This is this covariance matrix sigma that I'm using very concretely for this example on the left-hand side. Well, and now, this is a Gaussian, so I can actually plot this Gaussian. This is what I've done here. You see this ellipsoid here. This is just one isocontour of the Gaussian. And I've plotted this particular joint multivariate normal distribution. That's what's meant to be this gray thing here that I've labeled prior. So this is the prior, but now I've made these observations. I've made the observation that y of x1 is 0. And this is why I am now cutting different color, which you see better. This is why I'm now cutting my prior with this plane here. And this plane is located at 0, because 0 was my observation. Along this axis, you see this axis here is x1. Now along axis x2, conditioning on the observation being 1, because here I found an observation of +1. So now this conditioning is located at 1. So I'm now intersecting my Gaussian with these two planes, and this is what's shown on the bottom. So this is my Gaussian intersected with these two planes. And now I could condition, here I have x3. This is the distribution that I will get for my third random variable. And now I could condition on one observation that would give me this Gaussian that we see here, or I could condition on the other observation, that would be that Gaussian, or I can condition on both. If I condition on both, I'm focusing on this intersection of the two planes. And well, now in fact, along this intersection, we again get a Gaussian distribution. Why do I know that it's Gaussian? Because, well, the conditional of a Gaussian remains a Gaussian. And this is easy to see if you write down the Gaussian and just fix some of the random variables. So this is the distribution that I'm getting out for my third location. I can summarize this distribution by just a single value. I'm saying, well, my best guess is that it's this, but I get more. I get this spread around my best guess also. And that is hugely important in Gaussian processes, that we do get this spread, that we do get this uncertainty estimate. Okay. I want to just show you this Gaussian a little more. And so I've created this isocontour, but in the program in which I created the isocontour, which is what my kids are using to draw pictures, I could not label the axes x1 and x2 and x3, so I've simply labeled these axes dog and cat and fish. Okay, so dog is x1 and cat is x2 and fish is x3. Here we go. So let's look at dog versus cat. You see, here's my ellipsoid. Yeah? It's just one ellipsoid of my Gaussian, or one isocontour of my Gaussian. If we look at dog versus cat, How do I pan? Yeah, like this. If we look at dog versus cat, so dog is down here, cat is this axis, we see that we have a strong positive correlation between dog and cat because they're at a distance of just 1. Similarly, I can look at cat versus fish. Cat versus fish. I again get a nice strong correlation because they're at a distance of 1. Now we see that this is by no means an isotropic Gaussian. It's pretty strongly oriented along the diagonal. But now, so again, I'm not so good at drawing, so this is why I wrote here. This is dog and cat. Here, dog and cat and fish. And what we looked at so far was the amount of, or we were looking at this marginal distribution of dog versus cat in this prior, or cat versus fish, which was at a distance of just 1. But now I'm interested in dog versus fish. Yeah? So they're at a bigger distance. So I can read off from my RBF kernel. So this distance of 1 here, this is dog versus cat, or it's also cat versus fish. They're both at a distance of 1. But the dog versus fish is at a distance of 2. So let's look at that. Dog versus fish. I still have a little bit of correlation between dog and fish, but much less. That's what my RBF kernel is telling me, that because dog and fish are further away, I should have a smaller amount of correlation. Okay? So this means depending on how I turn this Gaussian, I get a stronger or weaker correlation between the different random variables that are associated with these 3 axes here. And by the way, here I made these x1, x2, and x3, I made them equispaced. I made them have the same distance, but there's no reason why they need to be at the same distance. They can be at any distance because my kernel function, or my RBF kernel in this case, will give me an answer at any distance. They don't have to be equispaced here. All right. Let's do one more example. The pictures on the left you've seen above. Those were priors from 2 different Gaussian processes. But now we actually have some observations. The observations here are marked by these dots. These are my observations. And now conditioned on these observations, I get for all other locations a Gaussian distribution. This Gaussian distribution, we could have drawn these marginal Gaussians. So we could have said that, I used this strange orange color before. So we could have said that at the site where we have measurements, my posterior has no spread. I get an infinitely narrow Gaussian. But here, away from my observations, I get a fairly wide Gaussian. But here, close to observations, I get a very narrow Gaussian. These are not properly normalized now, but you get the idea. Yeah? So the thing to watch here is the amount of spread. Here we have a large spread because we are making a prediction that's far away from the measurements. And here we get a small spread because there are 2 measurements close by. Now, instead of drawing these marginals, or these, the conditionals of the specific variable, given the labeled ones, what Andreas Krause and his co-authors in this paper here that I'm citing, what they have done is that they have made a conditional simulation. They have sampled a few realizations that are all compatible with the measurements. So in other words, going back to this picture here, instead of drawing this conditional distribution, they have simply sampled a few points from this distribution here, and each of these samples is amounts to one of these functions that you see here on the right-hand side. So this is a conditional simulation given first the Gaussian process with our assumptions for what's the mean, what's the covariance structure, and given these measurements. Now in the bottom, the measurements are the same, the very same. Yeah? So you see this point is this one, and that point is that one, and so on. The measurements are identical. However, here a different covariance structure has been assumed. On the top it was a radial basis function, and on the bottom it was this exponentially decaying covariance function. And again, a few conditional simulations are shown, and you see that here, if I try to summarize what the distribution or what the uncertainty or what the spread may look like between observations, it would look something like this. So I'm trying to draw an envelope here, which corresponds to, let's say this is plus or minus 1 standard deviation. It's probably a bit more drawn here. If I also draw a similar envelope here, we see that this envelope is much bigger or thicker, or the realizations of this conditional simulation are much noisier as we go away from our observations. And I've said before that these conditional distributions, we can always summarize them by their mean. So in the example here, instead of showing this whole pink curve, we can always summarize it by just its mean. If I show this mean here, sorry, I should have used a different color. If I show the mean, then these are these curves that we see painted a little bit thicker. Yeah, so both the prediction, the mean, is going to be different, but in particular also the estimated uncertainty is going to be quite different depending on what kernel I choose, depending on what covariance structure I assume. Yes?
But these observation lines that are drawn there, I cannot just sample for them at each point, because then I wouldn't get a continuous line, right?
I didn't understand the question. I'm sorry.
How would you generate one of the small lines, one of the faint gray lines?
In the simulation?
Yeah.
How to make a conditional simulation?
Yeah.
Okay.
Because you can't just go there and sample at each point, because then you wouldn't get a continuous line, right?
Well, in practice, we always only draw a finite number of points here. So what I can do is I can take my covariance structure, I can factorize it, and then I can use that to smooth over white noise in order to create one of these realizations. Yeah, so in practice, what I would do is I would generate white noise at a given discretization, and then I would smooth it with the appropriate smoothing kernel that I can compute and that has a one-to-one relation with the covariance structure that I'm assuming. And this is easy in 1D. It's harder to do this in multiple dimensions. So how to generate good conditional simulations, there are various methods, but it's all a little more complicated. That's one way of looking at it. The other way is just to say that we always compute this conditional distribution and sample from it. But the question is how to do this efficiently. All right. So that's the explanation in pictures. And now, this was all very nice in pictures, but now we would like, a real recipe. Yeah? So, given some assumption for the mu and sigma, given a couple of measurements, how would I then estimate these thick lines? And how would I estimate the amount of uncertainty, which I've here indicated in red, over space? So we've done inference in pictures, and after the break, we will do the inference in proper math.